Hi guys, welcome back. So in today's video I want to cover the technique called T-SNE, which basically stands for T-distributed stochastic neighborhood embedding, all right? So what T-SNE is basically a dimensionality reduction technique like the PCA that I covered in one of the previous videos. And T-SNE is actually a very powerful dimensionality reduction technique, and it's particularly used for visualization. Okay, yeah, it's particularly used for visualization. And I'll explain exactly what it does geometrically and intuitively, but I will not be covering the mathematics behind the technique in this video, all right? Because there's a lot of ground to cover for that mathematics, a lot to cover in probability and stats, and I'll probably cover all of that in different videos before I delve into the mathematics behind T-SNE. So T-SNE was discovered by Geoffrey Hinton, who was the godfather of artificial intelligence, in 2008 at the University of Toronto. And I'll try and explain what it does and the advantages it has over PCA, all right? Both of them do the same thing. They are used for dimensionality reduction, but T-SNE preserves the local structures in the data set as well. Okay, I'll just explain what that is in a minute. So let's take, for instance, that these are our data sets. Okay, this is our data set, and these are our data points in the data set. And let's just assume that this is a d-dimensional data set. Now, obviously, I can't draw a d-dimensional data set on in 2D, so you just have to assume that it's a d-dimensional data set. Now, what PCA will try to do, if I try to reduce the dimension of this data set using PCA, what it will try to do is it will try to maximize the variance. And in order to do so, it will project all of these points on this axis, right, to maximize the variance. So variance maximization basically tries to preserve the global structure of the data set. But as you can observe that there's also local structure in the data set. There we have these data points that form a local structure. And if we use PCA, then this local structure gets morphed onto the straight line, which reduces which is not very useful if you want to visualize your data set. If you want to visualize your d-dimensional data set into a 2D data set or 1D, right? So to overcome this problem of the PCA, we use T-SNE, which is T-distributed stochastic neighborhood embedding. Now I'll explain what the terms neighborhood and embedding mean, all right? So let's say that I have a 2D data set and I have these 4 points here, right? And these 3 points here, 5 points and 3 points. So a neighborhood is basically points. Let's call this point x1 and x2. So the neighborhood of x1 would be x3, x4, x5 would be x2, x3, x4, x5. All right. So neighborhood is basically all the points that are in close proximity to the point x1. Similarly, if I have x6, x7, x8 over here, the neighborhood of, let's say, x6 will be x7 and x8, right? Because these points are close by and they are. I can't say that x4 is x4 is in the neighborhood of x6 because these points are very, very far away on the data set, right? So this is what the neighborhood is. Basically, if the distance is small between 2 points, we can say that the neighborhood of points is very close. All right. Now let's go on to what I'll try to explain what embedding is now. So let me explain what embedding is. Okay, so let's say that I have just assume that this is a 2D space and this is a 1D space. And I have some points here, right? And when I embed these points from 2D to a lower dimensional space, which is 1D, I'll have an image of all of these points somewhere here. Let's call this point x1, and here I'll have x1 dash. Let's call this point x2, and I can have x2 dash over here. Let's call this point x3, and I can have x3 dash over here. So embedding basically means that if I have a d-dimensional space, for every point in d dimension, I'll create a point in a lower dimensional space as well. So I'm trying to find points in the low dimensional space for every point in the high dimensional space. So this is the process of embedding, right? So let me explain what the T-SNE is now with a geometric intuition. So let's say I have a 2D space and I have 4 points. Let's call this point x1, x2, x3, and x4. And the distance between all these points is d. So the distance between x4 and x2 is basically under root 2d, right? And this is a 2D space. Now, if I want to project all these points on a 1D space using T-SNE, okay, this is 1D. If I want to project them on the 1D space, what I can do is I can take x4 over here, and I can take x1 over here, I can take x3 over here, right? Because we can see that x3 and x1 are in the neighborhood of x4 because the distance here is d and d. But x2 is not in the neighborhood of x4 because the distance between x4 and x2 is root 2d. But x2 is in the neighborhood of x3 and x1, right? So where do I place x2 in this on this line so that the condition is satisfied? Well, this is what you call the crowding problem in T-SNE. The thing is, basically the crowding problem says is that I'll try my best to place all these points in their neighborhoods, but I will not guarantee it. So according to the crowding problem, there will be 1 or 2 points that don't get placed in the right neighborhood. So if we apply T-SNE here, x2 might come somewhere here, or x2 could come over here. But because of the constraint of this problem that it's a square, it will not get the perfect place between x1 and x3. This is a very common problem in T-SNE. It's called the crowding problem. And yeah, basically, T-SNE says that I'll try my best to place all the points in their respective neighborhoods, but I will not guarantee that I can do it. And yeah, so it'll place x2 either next to x1 or x3, but not at a place where it's equidistant from x1 and x3. Now, people can ask you that, interviewers can ask you, why not just place it on x4? Well, in that case, you can't do that because if you place it on x4, you say that x2 is in the immediate neighborhood of x4. But from here, in the two-dimensional data space, we can see that the distance between x1 and x2 and x4 is under root 2d. So you can't place x2 over here. So there will be a few points that don't get placed in the right neighborhoods, but that can't be helped. That's just a limitation of T-SNE. So basically, in very simple terms, what I do is the intra-neighborhood distances will be preserved, but the inter-neighborhood distances may not be preserved. Okay, so I'll stop this introduction video of T-SNE over here, and I'll explain the mathematics in the next video. Thanks.